So good evening. Today we will be starting with this digital filter, and within the digital filter, as I have been telling you, that there are two types of filters. One is FIR filter, and the second one is IR filter. Okay. So we'll be starting with FIR filter because it would be easier for you to grasp how to design the FIR filters and how to implement that. That is the one of the major problematic area for the students who want to design the IR filter. So if you do not have a grasping on the FIR filter designing, then it becomes difficult for you guys to understand the IR filter design. Okay. So before we start with the digital filters, because there has been a lot of gap, I will be giving you a recap on uh, what are the digital filters, and then slowly we will move into the consequent topics. Okay. So as we all know that digital filters, they are usually given or represented mathematically with the transfer function which is given by hz. Okay. And if you consider any analog filters, herein I have given the example of inverting non-inverting amplifier. Okay. Now if you look into the input and output relationship, it is given by v0 equals to 1 plus r2 by r1 into v1. Okay. So what happens if you bring this vi on the other side? So we get v0 by vi equals to 1 plus r2 by r1, and this is regarded as the gain of the filter. Okay. Now if you compare the gain of the filter and the iz, you will find that both are same. The only thing which matters over here is that in the gain, if you see, all the components that have been mentioned over here are the real components. Okay. So the values are real values. Okay. On the other hand, when we talk about the yz and xz, we have previously discussed that yz and xz, they are polynomials, and those polynomials, they are basically the complex functions. Okay. They are basically the complex functions. So why that complex function comes? That complex functions comes because we are having this frequency components that is associated with the filters. Okay. That are associated with the filters. Now if we made subtle changes in this r2 and x1, what are these are nothing but the impedances. Okay. Now instead of this r2, if we use xc or say xl, or a combination of xc and xl, that is also possible. And when you do that, what happens is that you will be incorporating complex functions within this equation. Okay. So then that equation, that gain what we are discussing over here, that will also become frequency dependent. Okay. So in that case also, if you see, the output would remain the same, or the gain would be remaining the same, v0 by vi, but in that case v output, it may be what you call dependent on the frequency. Also we can give the input, which would be a frequency dependent input. Okay. So and then if you try to compare this one and this one, exact, there would be no such difference. Okay. There would be no such difference. So basically when we talk about these transfer functions, these are nothing but your output by input relationship. Okay. Or the gain in the complex domain. Okay. Now coming, having an understanding of the filters, now if we consider the filters, in most of the filters, especially if you look into this non-inverting amplifier, there is a feedback loop through R2. Okay. So what is that feedback loop? Basically what it says, that if I want to calculate output, we have to take the output from here, and it will serve as an input to the inverting terminal, and we'll be having this input V in through the non-inverting terminal, and due to some operation that is happening within the op amp, we will get the output again. Okay, that means what we are doing, we are taking the present output and then we are using it to calculate the current output along with the V in. Okay, so when we use the present and the past outputs to calculate the present output, then it is regarded as the recursive filters or the feedback filters. Okay, so recursive, it stands for whether a system is having a feedback loop or not. Okay, similarly, the other class of the filters, they are basically non-recursive filters. Okay, so under practical considerations, when we try to design any kind of filters based on op amps, then we are basically designing the recursive filters, because we all know that op amps, they work within a specific range only and only when we are having a feedback loop. If there is an open loop configuration, then what would be the output? We will get an output which is getting saturated, right? I hope that all of you are able to understand. So what are open loop and closed loop gates? Okay, so these are basically, if you see over here, the non-inverting terminal, over here we are having a feedback loop. Okay, now this is called a closed loop system. Now if we are not taking any output from the op amp and there was no R2 over here and it was blank, then it would have been a it would have been an open loop configuration of the amplifier. Okay, so under practical considerations, as we have just discussed, that the feedback loop is important. Okay, the feedback loop is important. Now if it is important, so it comes with responsibility also, right? Just like if you are given with power, the power will come with some responsibility. Similarly over here also, when you are given with this feedback loop configuration and you can do a whole lot of activity. So if you are given with the power that you can do a whole lot of activity, but what will happen is that you have to design the filters with proper responsibility. Now, what is the responsibility? The responsibility over here is to place the poles judiciously. Okay, we have previously discussed that while designing the filters, we have to place the poles within the unit circle. Okay. Now, for the classification, I have been discussing about two terminologies: finite impulse response and infinite impulse response. We have previously already discussed about the impulse responses. What are the impulse response? Impulse response is nothing but, consider you are having a LTI system and then you give impulse input to the system and correspondingly you will be getting that output, and that output, it is nothing but your impulse response. Okay, now if you look over here, I talked about two words, finite and infinite impulse response. Okay, so that means when we talk about these FIR and IR filters, the FIR filters, they will be having a finite length of HN. So what we will have for FIR filters, the HN, that is the impulse response, it would be a finite sequence. That means the HN values will be there for indexes varying from 0 to small n. Okay, where n is a finite number. Okay, on the other hand, For infinite impulse responses, this HN sequence, it would be infinite. However, even though it is infinite, at time tending to, or say n tending to infinity, your HN values should be tending to zeros. Okay, so HN value, okay, that means you can say the output sequence or the amplitude. So A values, it should be tending to 0. Okay, for a system or a filter to be stable in nature. Okay, so this is the difference between the FIR and IR filters. And FIR filters, they do not have the feedback loop. IR filters, they will be having the feedback loop. And since the FIR filters, they do not have any feedback loop, if you look into the transfer function of FIR filters, they are quite simple. There are no denominator. Okay, there are no denominators. Unlike IR filters, which are complex systems, and you will be finding polynomials in both the numerator and the denominator. Okay. So, since we will be discussing about the FIR filter uh, in this chapter, so what happens over here? If you see, we will take a simple case of the FIR filter. Say Hz equals to 1 plus 4 Z inverse plus 4 Z to the power minus 2. You can simplify it in this form: 1 plus 2 Z inverse whole square. Okay. Now, if you want to find out the pole zero plot, we have already discussed how to do it. So, by this method, if you do it, you will be finding that there are two poles at z equals to minus 2, two zeros at z to the power minus 2, and there would be two poles that would be within the origin. Okay. Now, when you talk about this, so talking about the stability of the system, we have already discussed that for a stable system, we have to put the poles within the unit circle. So, in FIR filter, where are the units? Where are these poles? If you see, all of them, they are in the origin. Okay, all of them, they are in the origin. Now, due to this reason, FIR filters, they are inherently stable. They are inherently stable. Whatever you do, you cannot make an unstable FIR filter. Okay. So now look into the implementation of this filter. How do you realize it? So we are given with Hz equals to 1 plus 4Z inverse plus 4Z to the power minus 2. So Hz can be broken into yz by xz. Now, if you simplify it, you get yz equals to xz plus 4z inverse multiplied by xz plus 4z to the power minus 2 multiplied by xz. Okay, so how do we implement it? Now, see, there is a direct relationship between yz and xz. So, conventionally, we put input on the left hand side and output on the right hand side. So, we have put xz and yz over here. Now, since it is directly proportional and there are no multipliers in between, okay, so there is a direct relationship. Xz will come to yz. However, there would be a adder for the subsequent thing. So xz goes to an adder, and the output of the adder would be the yz. Now, next one is 4z inverse xz. So there is one z inverse, so the input will be delayed. So we will take a branch from the xz. It is delayed. Then there is a multiplier of 4. There is a multiplication of 4. Then it goes to an adder. It goes to an adder, and from here it goes to yz. Okay. The third term is z to the minus 2. We already have z inverse, so we have to implement another z inverse, and then from there is a multiplier of 4. Over here it goes to the adder, and we get the output y. Okay. Now let us see whether our realization is correct or incorrect. Okay, so when I talked about this impulse response, I told you the input would be the impulse input. So impulse input means at n equals to 0 we will be having 1, and at all other time instances the values would be 0. So delta n equals to 1 0 0 0 0. Okay, now let's look into the output values. So we have put several points a b c d. Now in a, when we are giving the input at n equals to 0, क्या है 1. Okay, b, there is a delay. Previous to 1 what was there? 0. So 0 it will be there. In c, 2 delays, 0. Okay, so what would be the d? D would be 1 plus 0 plus 0. So you get the 1. Okay, similarly in the next instance, at point a we are having 0. At b, this 1 will be coming through this delay. Okay, this 0 will come to c. Okay, then what would be the output? See, 1, b is 1, 1 multiplied by 4, 4, and at other two terminals it is 0. So we get y equals to 4. In the next instance, at a we will be having 0. This is 0. This one will come over here. This one at c, it will be multiplied by 4. So we will be having 4 plus 0 plus 0, 4. Now as you go on increasing this on the right hand side, you will find, so over here we are having 0, here we are having 0, at c we are having 0, so ultimately at d we will be having 0. And if you still go on, you will be finding that the values are 0 0 0 and so on. Okay, so herein if you see the yz was having a finite duration. Okay, yz was available only for a finite duration, and hence our filter is an FIR filter. And if you look into this coefficients, these coefficients are nothing but 1 plus 4z inverse plus 4z to the power minus 2. Okay, so what is this basically? This is h of n. And how do you find out the z transform? I already told you. It would be 1 plus 1, basically z to the power minus 0, plus 4 into the z to the power minus 1 plus 4 into z to the power minus 2. Right? So 1 plus 4z inverse plus 4z to the power minus 2. So you are getting the coefficients from there, which is what you call basically the coefficients of the filter that you started with. That means the implementation of the filter is correct. Okay. Now apart from this implementation, sometimes instead of the implementation we ask that you draw the signal flow graph. Now in the signal flow graph it is basically the same thing. However, these multipliers, they are being put by arrows, and there are no adders. Basically the point where all these points intersect, so that point is considered as the summer point, okay, or the adder point. Okay, so you see in your question whether it has been given implement the filter or draw the signal flow graph. So accordingly, basically both are the same thing, but uh, if implementation is told, you are being asked to implement the filter, then you have to do the draw the first architecture. If it is told that draw the signal flow graph, then you have to do the second one. Okay. Now, in our one of our last classes, we also discussed about this cascading of the filters, where there would be we will be having two subsystems and they will be multiplied with each other. Okay, so herein if you see what we have done is that our transfer function was basically 1 plus 2 z inverse whole square. So it can be written in this form and in this form. Okay, now this is subsystem A, this is subsystem B. Okay, now when we are having this multiplication, then it is called cascading. Then it is called cascading. Okay, now you implement A subsystem over here, you implement B subsystems over here, and you join it, and this joining part you can say as y dash or the intermediate output. Okay, and your final output will be over here. Okay, so now if you try to put the input output relationship, and if you give this um, input this impulse input where a is equal to 1 0 0 0, then our a b c d e, this should be 2. There is a mistake over here, so this should be 2. And again if you try to find out the output would be 144. Okay, the same way. So we have some time. So let's discuss this thing for 15 minutes, and then you can go for the practicing of those two sums. That will help you out. Now, while designing the FIR filters, we have to have some considerations. So what are the considerations? The considerations are that modulus of h of omega, it is regarded as 1. Okay, so why it is 1? Because in that case modulus of y of omega equal to modulus of x of omega. So we are basically making our life simple. Okay, we are basically making our life simple for the implementation process. Now the second consideration is that FIR filters, they are direct process filter designing method. So in IR filter, what happens is that we usually design a prototype low pass filter, and then we generally apply the frequency transformation method to get into the other to design the other filters like band reject filter, band pass filter, high pass filter, etc. Okay, so next is third one. This is related to the direct process. So it says FIR filters can be designed individually and separately. Okay, we don't have to depend on other types of the filter like in the IR filter. That's what I told you. Then coming to the point 4. So h of omega, the general representations of the filters are h of omega equals to capital M multiplied by e to the power minus j omega n. Okay. However, we have discussed that the magnitude of h of omega, it is considered to be 1 over here. So this equation simplifies to e to the power minus j omega n, which is equal to e to the power minus j theta, where theta is the phase component of the system. Okay, where theta is the phase component of the system. Now for FIR filters, if you plot theta phase versus frequency, then it is usually a linear system. Okay, so linearly it increases, and this is regarded as, due to this reason, FIR filters, they are regarded as phase linear filters or linear phase filters. Okay, now from here we can have time delay, and this time delay, it is given by minus of theta omega by omega. Okay, which is regarded as the uh, time delay. And there is another factor which is regarded as the group delay. It is given by minus of d theta omega by d omega. Okay, so this factor, it is regarded as the group delay. Time delay tau p, group delay tau g. Okay, now next is, for designing FIR filters, there are no specific rules. Okay, so we cannot design a FIR filter with actual cutoff frequency. Okay, and most of the cases, except Kaiser window method, we will also not know what is the order of the filter. Okay, so these two things we will not be able to prejudge. Okay, depending upon what we are getting, based on that we will have to design the filters. Okay, and why this happens? This happens because when we talk about FIR filter designing, the FIR filter designing is basically being done by trial and error method. Okay. Now, filter characteristics. Herein, the order of the filters, these are quite high. The order of the filters are usually say 50 or 100 or 150. It is usually more than 50 order. Okay, and since the order of the filter is quite high, the computational complexity is also very high. Okay. Now, these are some of the differences between the phase delay and the group delay. So, phase delay, it is nothing but the time shift experienced by each sinusoidal component of a signal. On the other hand, group delay is the basically the time delay experienced by the envelope of a modulated signal or a group of frequencies. Okay, so that's why the name group it comes into picture, and then the other parameters they have been discussed, so you can just go through that. So we have already discussed about this, that this all the poles they would be at the origin. Okay, then again the time delay and group delay, what are the equations? A note on this has been provided over here. Now there can be two types of filters. One is constant phase filter and linear phase filter. In the case of FIR filter designing, we have discussed that FIR filters are linear phase filters. Now, if you look into the constant phase filter, the time delay is and group delay, though both of them they are constant. However, in the case of linear phase filter, the time delay it is basically linearly increasing and decreasing. Okay, since this is a linear function, so when you again do the derivative, it becomes the constant. So in linear phase filter, time delay is linearly increasing and decreasing. On the other hand, the group delay it is constant. On the other hand, for the constant phase filter, the time delay and group delay both are constant. Okay, both are constant. So because of this reason, because this linear phase filter it is of utmost importance for the LTI systems, because when we talk about this biomedical systems, what we talk about LTI system, linear time invariant system. So what does that linear means? It means that we are designing a linear phase filter which is also time invariant in nature. Okay, so for biomedical purposes these constant phase filters they are not used. Okay, again some of the details have been given. Now coming to this, what do you mean by the linear phase filter? Suppose we are starting with a signal sine of 2 pi f1 t. So we are having this signal and it starts from origin. Now if we delay it, say by if factor tau, say for example in this case the if you look over here the tau is here. Now if you try to uh, trace it down to the origin, the signal has moved by a fraction of minus of pi by 2. Okay, so if you look over here, minus of 2 pi f1 tau, it is equal to minus of pi by 2. Now if you try to calculate the tau, it is nothing but tau equals to 1 by 4 of f1. Okay, 4 of f1. Similarly, if you increase the frequency over here f2 such that f2 is equal to 2 of f1, f2 is equal to 2 of f1. So here the signal has moved by pi radians. Now again, if you try to find out the value of tau and if you simplify it, you get 1 by 4 of f1. Okay, so in both the cases if you see they are the same. Okay. Now, if you plot it over here, f1 and f2, so we are having pi to pi. We have taken the minus of pi and this thing. So if you see, it is here and it is here, and if you try to join it, it is basically a linear function. It is basically a linear function. Now we have taken two restricting conditions, f1 and f2, where f2 was is equal to 2 of f1. But if you consider, since this is a linear function, if you consider any in between values, you will be having a linear component over here. You will be having the points on this linear line. Okay. Hence, this kind of filters, they are regarded as the linear phase filters. Okay. Now, mathematically, if you see, so the filter signal at frequency f1, it is given by 2 pi f1t plus 2 pi alpha f1. Okay. Similarly, for the f2 signal, it would be 4 pi f1t. So 2 pi f1. So no, 2 pi f2. F2 is nothing but again 2 of f1. So we get 4 pi f1t plus 2 pi alpha 2 of f1. Okay. So what is the phase difference over here? The phase difference would be this one minus of this one. So it is 2 pi alpha of f1. Okay. So some of the differences between the constant phase filters and the linear phase filters, which I have already discussed. So you can just go through this. Okay. So next is a linear phase filter. So a linear phase filter, it refers to a type of filter where the phase response is a linear function of frequency, which I have already seen. So key characteristics of the linear phase filters: linear phase response, constant group delay, we already discussed. There would be no phase distortion as a result of the linear phase. And lastly, FIR filters, they are designed to have linear phase by ensuring their impulse response is symmetric or anti-symmetric, which guarantees this finite impulse response, this linear phase response. Okay. So types of the filters. The types of the filters can be of four types of FIR filter: type 1, type 2, type 3, and type 4. In type 1 and type 2, the coefficients are symmetric. In type 3 and type 4, the coefficients are anti-symmetric in nature. Okay. So what are these? We will be discussing at a later stage. So type 1 will be having an odd length of the filter coefficients. Type 2 will be having the even length of the filter coefficients. Likewise, in type 3 we will be having odd length, and type 4 we will be having the even length. Okay. So these are the four types of the filters. Now, if you see, in type 1 we are having even length. So odd length, sorry, odd length. So if you see 0, 1, 2, 3, 4. So length is 4. So we are having length is 5. So we are having 5 coefficients, and the center point is 2. So across these two, you will be having values which are similar to each other. Okay, equal to each other in fact. In type 2, the center point would be somewhere in over here. So an imaginary line. So across this center point, the values would be the same. Okay. In type 3 and type 4, if you see, the these points, they are in the positive one half, and the other points, they are in the negative point. Over here, also in type 4, we are having positive values, and then after the symmetric imaginary symmetric line, we are having the negative values. Okay. So again, the same thing, the type of filters and what should be the impulse response ring, even or odd, whatever. Okay. Now over here, if you see the different types of the filters, if you look into the type 1 filter, it is the most versatile filter, and using this filter you can design low pass filter, high pass filter, band pass filter, and band stop filter, which is not the case with the other types of filters. Hence, in most of the textbooks you will find that the FIR filter designing that has been discussed with respect to type 1 filter, and accordingly we will also stick to type 1 type of filter. Okay, so again, the implementation of the filter, suppose you are given with an HZ, how will you implement? We have already discussed, and this type of implementation, it is called the direct form of realization. That is called the direct form of the realization. Whatever I have just discussed few moments back, the same thing is being carried out over here. Okay. Now in the next case, linear phase filter implementation. Over here, what happens if you see these filters, it has taken this value, these are being taken as a in a U-turn, and if you look over here, how many yeah, the delays are there? The delays are 1, 2, 3, 4. Okay, which corresponds to our original delays. However, how many number of this adders are there usually? If you see 1, 2, and you can reduce one adder over here because it can go over here. I have added it just for the sake of better understanding. However, it can directly go over here. So the number of additions can be reduced to a certain extent. Now what happens? You are having this XZ, YZ is the output. You are having XZ. Then next one is okay, yeah. So this one and this one they are having a multiplier of 1. So we are taking the outputs directly from here, XZ, and from the Z to the minus 4, and we are adding it followed by multiplication. Okay, then 2 and 2 we are getting, so Z inverse, and after Z to the minus 3 we are taking the values, we are adding up and we are multiplying. Okay, and lastly after Z to the minus 2 we are taking and we are multiplying. So what we have done, first of all, we have reduced the addition, and secondly the number of multiplications have also been reduced. Okay, number of multiplications have also been reduced. So this linear phase implementation, this implementation, it is better than the direct form of realization. So from the next class, we will be getting into the designing methods. So you can now practice this implementation for both the things. Start with this one. And if you face difficulty, let me know. Then, okay. After this one, we will go with this one, cascade implementation, and then the last one.